All right, so this is the solution to the past question. Question 1C. So how many times does Bermain get printed and what is the time complexity? So here is the algorithm. So we have initialized I and S to 1. And while S is less than or equal to N, we increment I by 1. And now S is equal to S plus I. And we print what? Bermain. So Bermain, this function, this is the innermost function. Okay. So if you are to get the time complexity of this innermost function, then that's all. We've gotten our answer. So let's go about it. So you can see clearly that I is increasing linearly. Initially, so for the first iteration, we can see that I equals 1, then S equals 1. Okay, so after that, what happens? So for the first time, it is 1, 1. Now, I is incremented by 1. So I becomes 2 in the second iteration. And S becomes what? S becomes the previous S plus I. So S becomes 1 plus 2. That is 3. Okay. Now let's do the third iteration. We can see that I becomes what? 3. It's increasing linearly. So plus 1 plus 1 plus 1. Then S will become S plus I. That is the previous value of S plus I. So plus the new value of I. That is 3 plus 3. So S equals 6. Last one, fourth iteration. So for the fourth iteration too, we can see I is 4 since it's incrementing by 1, and S will go on to be S plus I. That is this previous S, which is 6, plus the current I, which is 4, so 10. So right now, the point of we doing all this is to get a pattern out of it. So you can see clearly that there's a formula for this: 1, 3, 6, 10, 15, continuing. So what's the formula? This is simply the sum of the first natural numbers, first n natural numbers. So you can see if we are to add, let's see, so the first 4 natural numbers is 1, 2, 3, 4. If we are to get the sum of this, so 1 plus 2 plus 3 plus 4, we will get 10. If we are to find the sum of the first 3 natural numbers, so 1, 2, and 3, we'll get 1 plus 2 plus 3, which is 6. If we are to get, let's see, the 13th natural number, so we'll go 1 plus 2 plus 3, no, okay, the 10th one, we'll go 1 plus 2 plus 3 plus 4 plus 5 up to 10. And this answer will give you 55. So there was this guy that got a formula for it, Fibonacci, Leonardo. He got a formula for this at a very young age, and the formula is S. So the sum of, we can see that S is increasing, as I said, as the series of the sum of first n natural numbers. So we can say that at the kth iteration, I will be equal to K and S will be equal to, so let me put in that formula: K times K plus 1 all over 2. So the formula is actually N times N plus 1, but here we are using K since it's the kth iteration. So those that don't really get it, let me show this. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. If you are to solve this manually on a calculator, you get 110. Sorry, you get 55. You get 55. Yes. And let's put it in our formula. So this is sum of first 10 natural numbers. We ended at 10. So S of 10 should be equal to 10, that is our k here now is 10. So 10 times what? 10 plus 1, that is 11, all over 2. So we can see that this becomes 110 divided by 2, giving you 55. So our formula works. So that is it. So now that we've gotten a formula for S, we can compare it with N, because the loop will stop once S is less than or equal to N. Okay, so let's go on. So right now we are at the kth iteration. I equals k, S equals k times k plus 1 all over 2. So what do we do next? Now, to stop the loop, what should happen? S should be less than or equal to N. So our new S is what? Okay, let me write it. S should be less than or equal to N. Now our S is equal to k times k plus 1 all over 2. So it should be less than or equal to N. Okay, so let's solve this. The top equation will be k squared plus 1. Sorry, k squared plus k. Yeah, k squared plus k. And let's cross multiply this. So it's less than or equal to 2n. Okay, now in asymptotic notation, usually we don't consider the variables, the ones with lower complexity. So you can see that comparing k and k squared has a higher order than the k. If we have a value like 10 squared will become 100, and k will become 10, just 10. So the squared is increasing way faster than it, so we consider that most. So here we'll ignore the k to make our calculation simple. So we can see that k squared is less than or equal to 2n. Okay, so now what do? We are making k the subject. So k will be will be less than or equal to square root of 2n. So this is it. This is when it will stop. So the loop will stop when k is actually greater than square root of 2n. That is it. Okay, so the loop stops when k is greater than square root of 2n. And now, how do we go about finding the time complexity? So from here, it's very simple. The time complexity, as I said, we represent in asymptotic notation, and we don't consider the constants like the ones with the lower order. So a constant is of lower order than the linear the variable here, n. So because of that, the time complexity is big O of square root of n. We omit the 2 since it's only a constant. It won't influence it that much. Alright, so the question was to determine how many times Bermain gets printed. So Bermain will get printed square root of 2n times. Square root of 2n times. That's it.